Hello and good afternoon from Germany. A warm welcome from my side. I'm Jens Flügge, and together with my colleagues Ute Kaufmann and Stefan Werninger, I'm very happy to welcome you to our SCHWIND webinar in cooperation with CSO. All right, so I'm very happy that we have CSO on board on this event or this meeting. And we will start with Francesco Versaci, who will talk about the Aberrometry and its principles. I'm very happy. Thank you very much for being here, Francesco.
And hello, thank you for inviting me.
My great pleasure. Please go ahead.
Okay. I would like to thank the SCHWIND company for inviting me to this presentation. Today we are going to talk about the Peramis device, which is our Topography. Is quite amazing and exciting device, but it's a bit complex. So maybe we have to start from the beginning, talking about its working principle. What I'm doing also during the presentation is to provide some comparison with the device that are in the market, and last but not least, we will try to have some clinical application and to review some interesting cases together. Okay, let's start from the very beginning. An Aberrometry is a device designed to measure aberration of the eye. Aberration word from Latin means to run from or to deviate from. That is exactly what the optical aberration does. If you look at this image, you will see that every rays that enter the eye is focused exactly in the same position. So every ray that are creating the image into the eye hit the retina in the same point. This is an ideal eye, but if we look at a real eye, you don't have the situation, and the rays are hitting the retina in different positions. So, as you can see in this definition, we have aberration. So some light is spread out over a region of the retina rather than being focused in a single point. Let's introduce at this point the concept of wavefront. Wavefront is a surface over which an optical disturbance has a constant phase. So rays and wavefront are two mutually complementary approach to light propagation, and the wavefront is always perpendicular, always normal to the rays. So if you observe this picture, the only surface that is always perpendicular to the rays is a spherical wavefront. But if we define an aberrated bundle of rays, we cannot have this condition anymore, and so we have that this wavefront, so this orthogonal surface, differ from something to the sphere. We call wavefront error the difference, so the path difference between this actual surface and the ideal surface. So actual minus ideal is the OPD. From the principle of reversibility of the light, we know that we state that if the path of the light is reversed after suffering some number of refraction, it will retrace its path back, which means that ideally I could use the reflection of some light on the retina, and this spot of light will act as a light in itself, and the way the rays will follow to exit the eye will in this path they will acquire exactly the same aberration that the light acquire in the path into the eye. So according to this principle, we can define the wavefront error starting from what the eye is providing as reflection, and in this case, the wavefront error would be considered minus the OPD, so the ideal wavefront minus the actual wavefront. If we want to give a historical background of such kind of devices, we have to start from 1619 with Christopher Scheiner, who set the base for the modern aberrometry. This German astronomer invented a kind of disc such that with two pinholes, and if the eye was aberrated, looking far light through those two pinholes, the images of the light was appearing with two distant lights. In the 1858, we have to report that Jean-Baptiste Leonfoucault invented or announced his knife edge test to measure the shape of conic optical mirror. We have to recall this because actually our optical principle is derived from the experience of Foucault. At the end of the century, on the 1894, Scherning invented his own method based on the projection of a grid onto the retina. In 1900, Johannes Harman find a way to measure isolated rays, and this first step has been completed a few years later from Schack, who invented the Harman-Schack sensor, but we'll see this in a few. In the 1930, Fritz Zernike, working on a set of polynomial to map the wavefront, invented the name of the way of mapping aberrations with a polynomial that takes his name. So in 71, Roland Schack completed the work of Harman by defining the Harman-Schack sensor, probably the most common sensor in both in astronomy and ophthalmology. Finally, in the 1995, Roberto Ragazzoni invented the pyramidal wavefront sensor. Roberto is the only one that among this person that I had the chance to meet in person and the honor of to meet in person, and he inspired the development of our barometer. So if we try to explain how our barometer works, we have to start again from the projection of the ray of light that light up a portion of the retina, and this portion of the retina reflects back light and behaves exactly as a spherical point source. So the light exiting the eye acquire all the aberration of the ocular media, and with the device we have to measure such aberrations. The optical system scheme for our device is something like this. We have a first plane that is conjugated to the retinal plane, and a second optics create a second plane that is conjugated to the pupil plane. We recall you that a conjugate focal plane of a given plane is a plane such the point of the first plane are imaged on the second one. Okay, so in the red plane I have an image of the retina. In the blue plane I have an image of the pupil. Now, and this one is the invention of Ragazzoni. If we place when I have the retinal plane a pyramidal glass pyramidal part, what I'm going to have is not a single pupil image of the pupil on the camera, but four images of the pupil. I'm going to call those pupils subpupils. Okay, and what we are trying to do is to try to understand if we can find a way to correlate the aberration of the eye by the properties of those 4 subpupils. To do this, we are going to analyze a single ray belonging to the bundle of rays of the wavefront, but this does not imply that we are losing of generality, because we could apply the same approach to every single ray belonging to the bundle. Okay, if the ray is a metropic ray, so with slope equal to 0, by definition, this ray is going to impact on the pyramidal on the pyramid exactly in the middle, which means that the pyramid is going to split the energy in 4 equal parts, and when I'm going to image those 4 subpupil, the point in correspondence to the pupil point that we are measuring is going to be with the same energy in all the 4 subpupils. This because the amount of energy that goes on the face A is the same of the one that goes in B, C, and D. So the amount of light, the brightness of each point, each pixel of the correspondent to this point is going to be the same. But if, on the other hand, we are going to handle a myopic ray, so a ray that is not with slope equal to 0, but is a convergent ray, the conjugate plane is not going to be exactly in the position of the pyramid, but a little bit move on the left. This means that this ray is going to hit the pupil, the pyramid, not in the center, but a little bit below, which means that the C and D face will receive more energy than the A and B, and this means that the C and D points on the sensor will be brighter than A and B. The other way around, with an metropic ray, I'm going to hit, the focus will be behind the vertex of the pyramid or inside the pyramid, and A and B will be brighter than C and D. So it looks like we found a way to correlate the amount of light in each point of the subpupil to the slope, to the intensity, to the slope of the wavefront. So the slope creates some changes in the light intensity on the 4 pupil, and by means of this simple subtraction among images of the pupil, I can calculate the derivative of the wavefront along x and y. So the one in x is going to be the sum of the left subpupil minus the sum of the right subpupil, and the one in y is going to be the difference of the upper subpupil with the one the upper minus the below one. At this point, by means of a simple integration method, we can achieve the wavefront error. Refractive error. According to Nam-Tybos and Iskander publication, we have that a good definition of divergence, so now in our case, the refractive error, can be retrieved by means of this formula. And we can see that this formula is actually showing as a main term the derivative of the wavefront along x and y. We just see that we just seen that our wavefront is basically able to measure such derivatives, and so we could say that the first output of our wavefront is the refractive error of the wavefront. let's now do some kind of benchmarking, so some kind of comparison with the devices, with the optical principle that drive the devices that are in the market at the moment. 3 aberrometers still use the shading method. Those aberrometers are the Z-Wave and the Alcon aberrometer, so the Allegro. And those are using the pure shading. One device is using the ray tracing. The ray tracing is nothing but modifying zoning, so it's a kind of a dynamic shading, because instead of projecting a full grid of points, they project a grid ray by ray. So they do not risk any overlapping among rays, but it will take more time to have a single acquisition. That's why the Tracy device is measuring just 256 points that are few compared to the rest of the devices in the market. A nice method to measure the aberrometry is provided also by NIDEC by the aberrometer called OptiScan. And they use a kind of dynamic skioscopy. And last but not least, because it's the most spread way of measuring the wavefront, we have to consider the Harman Shack. So Harman Shack the Harman Shack technology is pretty simple. The wavefront is constituted by a lenslet and a sensor, a CCD. And when the wavefront hits each single lens of the lenslet, according to the local tilt of the wavefront, I'm going to have a spot that is proportional to the amount of the local tilt. So if I have a kind of planar wavefront, I'm going to have that all the spots follow exactly in the axis of the lens. But if I have some local tilt somewhere, my dots will be displayed somehow from the ideal position of this spot. So we can say that we can assert that the derivative of the wavefront along x and y are proportional to the shift of in x and y of those spots. So let's start comparing the resolution of the two systems. The resolution of the Harman Shack is pretty simple to be calculated, because it's simply the number of lens of the lenslet. So if I'm mounting the lenslet with 1,000 point, I'm going to have 1,000 sample. Very simple. And the spatial usually the spatial resolution, if we consider a 9mm pupil, is between 250 and 125. So according to the number of points, sure. The number of sample on a pyramidal wavefront sensor is nothing but the number of pixels in one of the 4 subpupils. So in our case, is 45,000 points, which means a great resolution compared to the one of the Harman Shack. So we are talking about 41 micron versus 250 or 125. This one is the reconstruction that a Harman Shack sensor provides. So you can see that we have rough squares on the color image in the middle of the printout. And this one is the same case with our wavefront sensor. So you can easily see both in wavefront error and refractive error map the rings of the diffractive lens that this patient has in place, and you can see every small deformation of the wavefront. Let me take the chance of this first slide to comment a little bit this display, because maybe we are going to see some of those maps or displays, and I want you to know what we are displaying and in what way. You can see on the left-hand side of the display the wavefront error. So the upper part is the total map, so map of all the aberrations, and this can be divided on low order aberration and high order aberration. So the two maps, the two small maps under the big one are the low order aberration, so what you can correct by means of spectacles, and the high order aberration, that is what you cannot correct by spectacles. We have exactly the same representation on the right hand side, but instead of having the wavefront error, we are showing the refractive error in total, low order aberration, and high order aberration. Okay, so since we are going to see many of those maps, I wanted to explain a bit what this display is showing. The dynamic range saturation. We know that there are a limit for all technology to the maximum slope that an aberrometer can measure. For the Harman-Schach sensor, this limit is when a single cell, so this cell here, the red circle, receive instead of one spot, two spots, because the spot of the below cell is too displaced respect to his axis that he ends up in the neighbor one. We have something similar that happen in the pyramidal wavefront sensor when we have some part of the wavefront, some local tilt that are so strong and so high that all the energy fall in one single quadrant of the pyramid. So if I have that all the energy for the point that I'm taking into account falls into one single face of the pyramid, all the energy will go in one of the subpupil for this point. And so if I do the calculation at this point, I'm going to have that the wavefront along X and along Y is 1, and I cannot see a real shape. So I'm underestimating the real slope of the wavefront. So how we can correct this and how we can avoid this? For the pyramidal wavefront sensor, it's pretty easy. We simply have to choose a retinal spot size big enough to cover for every slope the four face of the pyramid. So if I have the same amount of local tilt, in this case I'm hitting also the face B, C, and D, and so I won't have one, so a saturated situation of the derivatives. What about the Harman-Schach wavefront sensor? We know that the maximum slope that we can measure is proportional to the size of each cell, and so if I want to reduce if I want to increase the dynamic range, so I want to reduce the probability of some saturation, I have to increase this dimension, which means to increase the size of each lens, which means to decrease the number of points into the lenslet. So dramatically, the dynamic range is has an inverse proportion with the resolution of the device. So I cannot achieve the two at the same time. Let's talk also about the way we use to retrieve to calculate the wavefront from in those two technology. I just see that the title are inverted respect to the description. So what actually happened in the Harman Shark that we have to do a kind of model reconstruction. So use a Zenek fitting or some kind of fitting, and we can achieve the wavefront image just offline. What actually is happening in the pyramidal wavefront sensor is that we don't use a model reconstruction, so we can go with a direct integration method. This because our samples are so dense that we don't need to have a sampling model. The direct integration methods are usually very fast, and so we can have 30 frames per second and real-time reconstruction of the wavefront. What I'm showing now is the wavefront of a colleague of mine, younger than me, that is accommodating during the measurement. So I asked him to accommodate during the measurement, and you can see how the wavefront change according to his effort to accommodate. So now he's accommodating, and you can see the spherical power changing on the wavefront. As a reflex of this, we can also, this is one of the nice features that we are offering in our device. We have also the chance to measure the accommodation of the patient by means of two exams. The first exam use a kind of rectangular signal, and so I see an object optically at the infinity, and then suddenly it come closer, and I'm asked to accommodate to see it sharp and focus. And then I have to release again the accommodation because it goes again at the infinity. And this one is the one on the left. The one on the right is the stair. So in the stair, I'm measuring what is the residual accommodation of the patient. So what I'm doing is to start with an object that is projected from the infinity, and then the accommodation request increase of 1 diopter for each step, and I'm asked to focus step by step this target. So this is to check how many diopter of accommodation I can provide. Usually, the one with a square wave is used to check and to measure the delay of the patient in accommodating and deaccommodating, and the one on the right is used to check the residual accommodation. Let's see some case of clinical application of the device. First of all, and I think that is also the main reason of the device is the customized refractive surgery. But due to the very high resolution of the device, we can use the device also to manage very complex cases, and we are going to see a couple of them. Last but not least, we have to think about using the device when I have an IOL or in general some kind of lens into the eye. This because when the issue is a corneal issue, I ideally could use a topographer, and there are some reasons why maybe for if the issue is corneal, it's better to use a real corneal topographer instead of an aberrometer. But when the issue is actually due to the internal part of the eye, there's nothing I can do with the topographer, or at least the only thing I can do is to use the information to remove the corneal influence from the total aberration of the eye. But we are going to see some example on the next slide. So talking about customized refractive surgery, this one is a case that has been provided by Jorge Alio. You can see that this one is starting wavefront. What I can do with this device is to measure the the aberration of the cornea, of the eye, and check what's going on if I remove some Wernicke components. So in this case, I just moved the low order aberration, but the quality of the vision is not, in any case, is not satisfactory. So this treatment is not enough. This information is based on the quality of vision and mainly on the PSF. The PSF is the simulation of how the eye perceive the light coming from the infinity. So the light from a star. So if the light is going to be very small, my Strel ratio, that is the way of measuring the quality of a PSF, is going to be high. If I have some aberration and the quality of the vision is not that good, my Strel ratio is going to be low and the PSF is going to be spread. So in this case was not enough because the PSF was still bad. So the surgeon decided to remove some of the high order aberration polynomial. So he ended up choosing to remove the spherical aberration and all the third order, and evaluate that the quality of the vision was good enough, and also the wavefront was planar enough. So he decided to go in by removing those components for a customized treatment, and the treatment ended up like this. So you can see how similar is the achieved outcome respect to the theoretical outcome of the device. This case is another very nice case. It comes from London Vision Clinic. It's from Daniel Einstein. So this one is a case of central toxic keratopathy, and it's not uncommon to have in presence of this issue a lot of aberration and some scarring line on the stroma. And so here on the left we have those scarring lines acquired by means of a slit lamp, and exactly the same lines, so exactly the same information on the refractive error map. So this means that the device is able to capture and to see very small detail, very thin details that are hardly visible at the slit lamp. And here you can see them very easily. Something similar is shown in this slide from Francesco Versaci. So if you look at the refractive error on the right, you will see that there is a kind of circular shape. So you can recognize here the posterior capsulotomy, and since this pupil is not that big, this means that the posterior capsulotomy could have some effect on the vision. And you can also recognize some strands, some lines, and those are the bicular strands. So you can have very important details from the observation of this kind of maps. This is also a slide from Francesco, who enjoyed a lot on showing the different power map of implanted IOL from normal spherical plano lens to EDOF lens, or lens that are having some kind of aberration like the IOL or the Lucidus. So by the observation of the refractive error of each of those lenses, you can understand easily how this lens is working, and you can recognize the working principle and the effect of each lens. It's also very important the evaluation in our device when you have some kind of lens implanted of the decentration of an implanted IOL. So by means of this image, you can understand if the center of the lens was actually a concentric with the kappa angle, so the corneal vertex, or like in the right case, there is an actual concentration, and we have to proceed with some kind of surgery to realign the lens into the back. A very interesting topic that we are going to talk now is about the toric IOL rotation. As you know, it's very common to implant toric IOL when we have to correct some kind of corneal astigmatism during IOL surgery. And but sometimes the outcomes are not the one that we plan during the preoperative phases. So, as you can see in this case, this patient ended up with a different axis of the IOL with respect to the one that was planned. This one is the measurement of the wavefront after the implant, and you can easily see that there is some astigmatism, some residual astigmatism, and on the right image you can see that the axis is not the one planned. So you can even see the small dots of the marker of the IOL on the refractive map, on the refractive error map. So the surgeon decided for a realignment of this lens. So this one is a display of the ocular, the corneal, and the internal wavefront, and you can easily see that the internal wavefront is exactly showing the astigmatism of the lens. So in this case, the internal aberration is nothing but the implanted lens, because there's nothing else into the eye. And so this confirms the rotation of the lens respect to the expected position, and this is the angle that the surgeon have to correct the position of the IOL. So the surgeon decided to take the patient into the theater again. He rotated the lens, this time in the proper position, and the outcome of the perfect outcome of the surgery is shown in this map, in this display, where you can see that the ocular is planar. The corneal shows some astigmatism, like in the pre-op, but the internal this time is fully compensating the corneal one. So we have a perfect match between the axis of the planned and the axis of the implanted. We have a specific display for this kind of problem. So this is called the toric IOL assistant, and allows you to see both in terms of coefficients or in terms of maps, what is the corneal and internal astigmatism, and also give you the information about what is going to be the best achievable refraction. So to understand if the issue is an issue of toric power calculation, or is an issue of axis of the toric lens, and also give to you the chance of calculating the amount of rotation that ideally you have to provide to the customer if you want to realign it in the corneal axis. Last but not least, I would like to highlight this paper from Theo Seiler, who used in combination the SCHWIND laser to correct the aberration due to misalignment or generically issue happen after IOL implant. So there are a certain range of patient unhappy after the IOL implant, And what has been done is to correct those patients by means of customized refractive surgery, and by correcting the high order aberration and residual low order aberration to achieve the best correcting vision for this patient. And the results are, as always, awesome. I think that this was the last slide. I would like to thank you for your kind attention, and I remain available for question.
Thank you very much, Francesco, for this very excellent talk. Very nice. So I will ask my colleagues, are there any questions from the audience?
Yes, we have two questions. The first one is, what is the source of error in such measure? Does dry eye affect the accuracy?
Yeah, dry eye can affect absolutely the accuracy of the measurement, because if I have some breakup on the tear film, the light will pass through this corrupted part of the tear film, and the measurement won't be good. What is important to say that those cases are really simple to be identified, and we provide a movie during the acquisition, so you can see if you have a kind of breakup, and you can see that the wavefront is changing during the acquisition. In this case, you have absolutely to repeat the acquisition, because you risk to have bad information. So, on the other hand, I would say that it's pretty interesting to see how sensible is the device, even to the smallest breakup. And I'm always amazed on seeing this, because it matches the accuracy of the device and the fact that it's real time. So even if it's an issue, and I know, on the technical point of view, it's pretty amazing to see and to observe how the wavefront change quickly when you have a breakup.
So if you have dry eyes, would you recommend using artificial tears, Francesco?
If you cannot get systematically a good acquisition, yes. I would suggest to have artificial tear that are not altering too much the viscosity of the eye, because then I could have a bad effect on the wavefront as well. But if the viscosity is fine, this is something that I might be good. Usually, is enough to close the eye and to acquire properly the image after some blinks. Please remember that during the acquisition you can even blink. So if don't ask the patient to be still like this, because you don't need to touch your patient. You just can allow the patient to blink, and this won't affect in any case the measurement.
Okay, fine. And the next question was, what machine uses pyramidal sensor in the market?
Osiris, which is the same of Peramis. As far as I know, the only device that use this kind of approach is the one that we provide for CSO, so Osiris, or the one that we provide for SCHWIND Peramis, that are actually the same device.
Okay, thank you.
Well, thank you very much, Francesco. Then I would say if there are no further questions in the chat, then Ute, if you want to say something, I think your microphone is still off.
Okay, we received 3 more questions. One is related to diffractive IOLs. When measuring total wavefront with diffractive IOLs to the rings of the IOL do the rings of the IOL interfere with the measurements, and how does the laser treat the rings?
Okay, I'm not supposed to answer to that part of the question, because I don't think that is part of my duty. but I can answer about the first part of the question. As you know, diffractive IOL splits the wavefront in 2 or 3 or 4 different wavefronts. What we actually do is to measure the main one, so the one with the higher energy. So the other one goes out of focus. We cannot measure the four wavefront because we have just a pyramidal sensor, and we have to focus on the main one. So the wavefront is the wavefront of the main one, but a very high density of points in the refractive map show you exactly the diffractive pattern of the IOL, and make you understand if there are some refractive components, if the lens has the same power everywhere, or some area with more power to help focusing at the near distance. Any other question from the audience?
There's a question from minimum pupil diameter for total wavefront guided treatment.
This is something that probably I know, but you might ask, you might answer. As far, yeah, correct.
Okay.
Okay, I think that it's time for Simone to speak now.
Last question, I think.
Yeah, let's make it the last question so that we are right in time.
Okay, it is necessary to measure the posterior cornea aberrations if we want to correct the total aberrations of the cornea.
Okay, when you approach a ocular wavefront guided treatment, we are correcting the whole aberration of the eye, not just of the cornea. Okay, so this depends actually on what you want to do. If you want to correct the whole aberration of the eye, then it goes for an ocular treatment, and in this way you are neglecting the cornea and you are taking the whole aberration. Doesn't matter if they are from the front of the cornea, the back of the cornea, or the peripheral lens, or anything else is into the eye. Okay. If you are thinking to a corneal aberration treatment, in this case, you might take into account the two surfaces of the cornea. So instead of using the front corneal wavefront, you might use the total corneal wavefront that is derived by retracing from the first and the second surface. But I think that Simone is going to talk about this in his speech.
Okay, thank you.
All right, perfect. Thank you very much, Francesco. I will now ask my colleagues Ute and Stefan, are there any questions in the chat?
Yes, there's one question. So the question is it possible to measure or to detect a tilt of an IOL?
The tilt is measurable, but actually it's hidden. But what is most interesting for us is that the tilt usually induces a high order aberration, okay, because the tilt usually is compensated by the rotation of the eye. So is detecting the tilt itself is not really interesting, but what is interesting is to measure the high order aberration, like chromatic aberration, that the tilt is inducing. Okay, and this is the main topic, and this is actually what we measure and what you might correct by means of the laser, for instance.
Any other questions?
So far, there are no other questions. Maybe the auditorium would like to ask even more. Right now, there was another question to IOL tilt. Is there a way to select specific aberrations to treat?
Maybe you might be asking, you might be better to ask yes, but maybe Ute, Stefan, or Jens, you might ask this question. You are more adequate than me in answering.
Yeah, basically, of course, there's a way to select aberrations, but not inside the Peramis. You can play around with there, but if you really want to treat selective aberration, you would do that inside the SCHWIND CAM software. And maybe I can already announce that we are currently planning another webinar, which actually with the task of customized treatments. So this might be then following up on these questions you were having. So
yeah.
you will be
back into the question. What you can do actually is to select single aberration and see the impact on PSF and MPF. So if you want to have an idea of how each single aberration is impacting on the vision, you could select like in the slide that I just showed to you, the one of from Jorge Alio and the one from Theo Seiler. You can select the single Zenicke components and check the changes in the PSF in order to evaluate if it's something that is mandatory to be corrected or can be left untreated.
great, thank you. I have actually one question and regarding accommodation. Which stimulus would you recommend to use? The square one or the slope one?
No, okay. This depends on what you want to test. If you're using, if you want to test the neurologic part of the accommodation, you use a kind of rectangular stimulus. So very quickly you pass from infinity to a -3, so or -4, and so you can measure how fast you reach the accommodation level and how fast you release the accommodation when the stimulus back to the infinity. If you want to measure on the other side the amount of accommodation, you might use a kind of step test that starting from the infinity, the one diopter after the other one, and so you can test how much residual accommodation do you have.
All right, thank you. Then,
we do have in our questions, we have once more a question to Francesco regarding the IOL tilting. Maybe you can explain once more how to detect the tilt, or maybe how to use the IOL tool.
Okay, something that usually happens when you have a tilted IOL is that some other, let's say like this, if I have some tilting and the IOL is spherical, usually nothing terrible happens because you are not inducing any aberration, and for this reason the patient keep having a very good vision. Okay, so tilting and centration of IOL is not a big issue when the lens is a spherical lens. The big problem arises when you are trying to compensate with an ADOF lens the loss of vision from near, and so we are inducing, I don't know, in some way, some other aberration, or you are splitting the wavefront in different copies of the wavefront itself. So in this case, the tilting or the centration can give bad acceptance on the patient side. So the centering is easy to be displayed because you can check from the backscattered image the position of the center of the IOL in respect to the corneal vertex. So you have the reflex of the corneal vertex, and you can see the center of the rings, so you can easily see where is the centration of the lens with respect to the corneal vertex. In case of tilting, the the most interesting thing to be done in this case is to see the effect and aberration of the tilting of a lens. So usually the tilting is come together chromatic aberration, so you can see the amount of coma that this lens is this tilting of the lens is inducing.
Very good. Was this, or is there any other question?
Okay, we have other questions.
Please.
There's a question. You mentioned the Peramis projects much bigger spots to the retina. So it can see on every subpupil image. How many of these big spots are projected to the retina?
Just one. But since it's not like the tracing that project many spots together, but since we have a second plane that image the pupil, okay, I would need to back on the presentation, but the optical design is such that everything is mixed up on the pyramid, but it back to be separated on the CCD plane and on the pupil plane. So you have a mixture of rays in correspondence of the vertical pupil, but you can again split each component in this position when you are observing the 4 subpupils.
There are 2 more questions. One, I would refer to the simulation of higher orders. How do I know which higher orders to be treated? And maybe, is there something you would like to comment on the possible simulation charts in the device?
Yeah, to talk about what simulation have to be treated, we should introduce the concept of metric of the wavefront, because we have to understand what does it mean to have a good wavefront or a bad wavefront. Usually, something that is done is to check the quality of the PSF. The PSF is the simulation of how a light coming from the infinity hit the retina. Okay, so if I have a small spot on the retina, the vision will be great, good. If I have a big spot, I will have a blurred vision. Okay. So usually, what has been done from people who treat plan customized treatment is to select and unselect the coefficient of Zerike and check what is the amount of the focus on the focusing of the aberration on the PSF. So if it appears that by removing a single aberration, the PSF doesn't change that much, maybe it's not worth to correct it. But if the removal of a Zerike coefficient have a big impact on the simulation of the PSF, this one is something that we might plan to remove. Then there are other aspects that you have to discuss on the other side. So how much this impact on the depth of the treatment. But optically speaking, you just check how much is the impact on the PSF.
Okay, great. And I think there is one question left, which also is a nice link between the presentation of Francesco and Simone, because one of the participants would like to know how to separate corneal higher order information from the aberrations, especially IOL aberrations. So can you separate corneal and lens or
Yes.
IOL aberrations?
By definition, the internal aberration is nothing but the difference between the corneal wavefront, the total wavefront, and the corneal wavefront. So if I can measure the corneal wavefront and I remove it from the total aberration, I will have the impact of the internal part of the aberration. And this is very useful, for instance, when you try to measure the tilt of the rotation of the toric IOL, or when you try to measure the impact of some internal components to the eye.
Okay, thanks.
Very good. Thank you very much. Then I would say we move over to the next speaker, and I'm very happy that Simone is here with us, application guy from CSO. And Simone, are you ready?
I'm ready, I'm ready.
Perfect. Here you are.
So thank you very much for the okay, thank you very much for the invitation. My colleague Francesco talked about corneal, total aberrometry. I'm going to talk about the topographic part of of Peramis. So first of all, let's do a little historical background. We know that the first document reporting the study of corneal shape was dated 1619, and here Christoph Scheiner, for the first time, studied corneal surface as a reflecting mirror. In the next 2 centuries, based on this principle, 2 devices was developed. The first was the ophthalmometer. This device allows to measure the corneal curvature in the very central part in 4 points. Thanks to these devices, it's pretty easy to get the radius of curvature. The only thing that we need to know is the height of the mires, the height of the images of the mires reflected by the cornea, and the distance between these mires. And this device were able to provide corneal curvature in millimeter and in dioptries thanks to this relation. The second device that was developed more or less in the same years was the Placido disc. The Placido disc, as you can see from the picture, is just a disc with white and black rings with a hole in the center, with a convex lens to observe the image of it reflected by the cornea. This was the first qualitative way to analyze a big portion of cornea. Remember that ophthalmometer was able to analyze just a very central part of the cornea. Instead here, with the Placido disc, we are not able to measure anything, but we are able to understand the full shape of the cornea. The principle behind the Placido disc was really simple. More the rings reflected were close, more the curvature was steep in the point, and more the rings was far one to each other, more the curvature was flat in this point. Here in the picture we can appreciate even the typical cases of first of astigmatism. This is the way of the cornea reflect the rings of Placido disc in an astigmatic eye, and this is the way that the cornea reflects the rings of Placido rings in a keratoconic eye. Here I reported a brief timeline of the history of Placido disc from the first development in 1880. Then, in my opinion, one of the most important steps was in 1896, where, thanks to a study of Alvar Gustrand, was developed an algorithm to take a measurement from Placido disc. 30 years later, Decking developed the first conic Placido disc, so a Placido disc that has a shape more similar to the one that we are using to see nowadays for the topographers. Another important step was made in 1979, where it was the first combination between a Placido disc and a computer to automatically measure the corneal curvature. And finally, the last step was in 1984 when Stephen Kleiss published a paper reporting a two-dimensional color-coded map for the topographer. So let's analyze together this color-coded map that was, of course, the sagittal map or axial power map. The meaning of this map is really simple. This map describes the curvature using a simple principle. The curvature in these maps are described point by point as the distance between the point and the optical axis along the normal direction. To evaluate this data, the topographer at the time uses like a comparison principle. So first of all, the topographers had to be calibrated with some calibration sphere of known curvature. Then, acquiring the sample, acquiring the cornea, the instruments did a simple comparison between what was known and what is the new sample, and in function to that, the curvature was carried out. In this map, the steeper points are reported with warm colors, and the flatter points are reported with cold colors. 10 years later, the publication of Stephen Kleiss with the large diffusion of refractive surgery treatment, many surgeons complain for a low accuracy in this kind of map, especially in the periphery of the reconstruction of the cornea. These are a few papers, but even other authors had this kind of problem in the representation of corneal shape. They wanted to have a local curvature, a more accurate curvature even in the periphery. And the answer of manufacturer to these papers was the development of a totally new algorithm to reconstruct not just the curvature, but even to describe elevation and refractive power of a cornea. This algorithm needs to know, first of all, I have to say that analyze cornea meridian by meridian, so a different way to analyze the cornea shape. And the only thing that we need to know is the position of the Myers on the placido disc, the position of the reflected Myers by the cornea, and the working distance of the instruments. So knowing these three things, as you can see from the animation, the software, thanks to a ray tracing procedure, is able to detect the normal to corneal surface. And once the normal was knowing, an algorithm allow us to reconstruct the corneal profile using arc of circles, as you can see from here. And this is like the definition of instantaneous curvature. So the instantaneous curvature is the radius of the osculating circle for each point belonging on the meridians of the meridian in question. So as you can see from this comparison, this is the main difference between the sagittal representation and the tangential representation. So in the center of the map, we could say that the indication about curvature are similar for these two representations, but going into periphery, we noted that the accuracy of tangential map is substantially higher. not just curvature, but even elevation can be described thanks to this algorithm. The way to describe the elevation is, let me say, popular, because it's similar to the geographic cartography. Okay, so we are expressing elevation respect to something known. As in geographic cartography, the elevation are expressed respect to sea level. In our case, elevation are expressed respect to a reference surface. The reference surface, in the case of Peramis, can be a spherical surface, an aspherical surface, and an aspherotorical surface. The differences in terms of weight are reported by the color-coded map. Sorry, and the difference in terms of weight are reported in our color-coded map this way. So when the cornea stays over our reference surface, the map is colored with warm colors, and when happens the opposite, the map is colored with cold colors. So now I would like to show you some examples of an astigmatic cornea represented with the three different reference surfaces. So the first is the spherical one that can be defined just with a radius of curvature. The other one is the aspheric one that can be defined with a radius of curvature and a coefficient of eccentricity. So in other words, a number that expresses how the cornea gets flat or steep going from center to periphery. And the last reference surface that is more similar to corneal shape, as you can see from the altimetric map, is the aspherotoric surface. So we have two radius of curvature of two aspheric surfaces to use as a reference surface. In this case, since we have a toric surface, reference surface, as you can see, the typical pattern of astigmatism cannot be visible in this case. Another important data that we can obtain thanks to the knowledge of the normals to the cornea is, of course, the refractive power. So, as I said, thanks to the knowledge of the normal to the cornea, we can apply point by point a ray tracing algorithm based on the Snellen law, and so we are able to understand even the power of the cornea point by point. The map of refractive power reported with warm color the most refractive zones, and with cold color the less refractive zones. This is an example of an application of refractive power map. So we can do the subtraction, for example, of two refractive power map of the preoperative and postoperative refractive surgery of a patient to understand objectively how many dioptries was corrected by the treatment. Okay, so this is the pre-op, this is the post-op, and this is the subtractive map. And in this case, we could say that we had more or less 6 dioptries of correction of the treatment. Another important data that we can carry out from the ray tracing is for sure the analysis of corneal wavefront. analysis of corneal wavefront, as Francesco explained before, is done usually thanks to the Zernike fitting, thanks to polynomial of Zernike. As Francesco said, the way to get the Aberrometry map is to do a comparison between two wavefronts. The first is the wavefront of an ideal surface. In the case of topography, we have an ideal cornea and a real cornea. So the difference between these two wavefront is defined as wavefront aberration, is defined as corneal wavefront aberration. This is a typical representation of OPD map. I like to say to don't be scared about this kind of representation that sometimes could be not so familiar. Try to imagine the optical path difference map as a cake, okay, and the Zernike polynomial pyramid as the ingredients of the cake. So what is the utility of Zernike fitting? The utility of Zernike fitting is understand which are the components of this cake. Okay, so let's analyze briefly which are the main components of this pyramid. First of all, let me do a classification of low order aberration and high order aberration. The low order aberration are the one over this black line and are the aberration that can be corrected by spectacles. So the sphere, myopia, hyperopia, and the astigmatism. The high order aberrations that cannot be corrected by spectacles. Once again, just to describe the main aberration reported here. Here we have the spherical equivalent. So what is myopia and hyperopia? Here we have the astigmatism. Here we have the coma aberration that we are going to describe, and the spherical aberration. So starting from astigmatism, this is an aberration that occurs mainly when the two main meridians of the cornea have different power, okay? This is the visual outcome of an eye, or in the case of topography, of a cornea affected by astigmatism. Now I'm displaying the spherical aberration. The spherical aberration is an aberration that occurs when a bundle of rays that meets the cornea are different positioning of focus. In particular, when the rays that incides in the central zone have a different focus respect to the ones that comes into periphery zone. The spherical aberration have two different effects on the visus. The first, as you can see from here, is a loss of contrast, and let me say this is the worst effect. But we have even a good effect that is an extension of depth of focus of the whole system. And to explain this that I'm saying, I want to use this example where we are doing a comparison between a diffraction limited system, so an aplanatic system, and another system affected just by spherical aberration. As you can see, starting in this condition, the aplantic system is way better respect to the other. But let's try to put in front of the two systems a minus 0.50 diopters lens. As you can see, for the smaller letters, the eye with spherical aberration has a better resolution respect to the other. And this thing can be noted even if I'm going to increase the power of the negative lens. So this is a quick explanation of what I've just said. So that the spherical aberration can give to our system an extended depth of focus. This is the last aberration that I would like to talk. It is the coma aberration. It is an aberration that occurs in the eye, mainly when we are in front of keratoconus, and takes the name from this shape, the shape of PSF, that it is a shape that reminds of a comet. And so from this the name coma. The effect of coma on the visus is really disturbing, because this aberration causes some mellows close to the letters, as you can see from the simulation of visus, and it's pretty hard to correct, because as I told you before, we cannot use spectacles. So the only way to correct this aberration is to regularize the surfaces affected by coma. Okay, so now let's change totally topics. Let's talk about the major acquisition. That it is one of the most important things that you have to pay attention when you are acquiring an eye. The first thing that you have to pay attention is the correct focusing of the system, because as you remember, I told you before that one of the things that we have to know to apply the ArcStack algorithm was to have a known operating distance. Okay, and how can we give to our device the good operating distance? The only way that we have to do that is to align these two slices of light, is to overlap these two slices of light. Okay, so this is a good way to respect the focal distance of our device. Another important thing that you have to pay attention, and I heard before from the question, it is a hot theme. It is the tear film. The tear film, talking about keratoscopy, let me say, is even more important respect to the aberrometry, because here, pay attention to the central part. And first of all, as you can see here from this keratoscopy, the quality of this tear film is really poor. I want to focus your attention in the central part. So this ring that is affected by the reflection of this ring is affected by low quality of tear film. This is what the algorithm of tangential curvature said about the central curvature of this cornea. I asked the patient to blink twice, and immediately after the blinking, I took an image of this cornea. So as you can see here, we have no artifacts due to the poor quality of tear film, and the astigmatism that was visible here, it is magically disappeared. So these two slides are to let you understand the importance of have a good tear film and a good ocular surface to be analyzed. Another important thing that you have to pay attention is the coverage of Placido disc. So the area that is interested by the reflection of Placido disc. This is a normal positioning of a patient, so on the chin rest, and as you can see from here, we have a big shadow that it is even reported over the fitting of this keratoscopy. How can we eliminate this shadow? We have a trick that we can do thanks to our chin rest. You can ask the patient to turn his head. If you are acquiring the right eye, you have to ask if he can turn his head on the left. It is easy to remind this because you have to think always to the opposite. Right eye, you have to turn the head on the left eye, you have to turn the head on the right. And using this simple trick, as you can see, you can get a fully coverage of Placido disc, so a good topography map. This is how our chin rest works. So this is the central position, and here, just rotating the chin rest with your hand, you can switch from left and right position. You don't have to be scared about let the patient rotate his head, because if the fixation of the patient, if the patient fixate the target, the internal target, as you can see from here, we are sure that the corneal vertex is perfectly aligned to the optical axis of the instrument. Okay, so let me use this slide to introduce this kind of report that you can get after all your acquisitions. So just going in the gallery over one acquisition and right click, you can get access to the statistics on acquisition. This is, in my opinion, a complete panel that gives you all the information that you need before to open an acquisition and to understand if the acquisition is good or not. So the first thing that this report says is some information about the quality of keratoscopy. So if you had or not a good tear film. The second information that you can get from here is the Placido coverage that we said is it really important, and information about the diameter of pupil that is important for aberrometry, because more the pupil is large, more the information we can get from the total aberrometry. Another important thing that we have to pay attention is the SCC value. That is a procedure that it is important to orientate the laser treatment. The SCC consists just in a frontal picture of the eye that is acquired before the topography. And thanks to this, SCHWIND can manage which will be the correct orientation of the treatment. To get this value better, it is suggested to cover the eye without touching it, because if you touch the eye, you can compromise the opening of the contralateral eye. So it is suggested to cover the eye and ask the patient to open wide. Okay, and you will get a good SCC value. Another thing that is reported in our quality acquisition summary is the standard deviation of SCHWIND. Your goal will be to have the lower standard deviation as possible. This means that you had a great repeatability of the measurement of SCHWIND. We can get even information about corneal astigmatism, and this is one of the most important things that this report can analyze, is the centration of keratoscopy. Okay, so this means that the corneal vertex is well aligned or not with the optical axis of the instrument. The best thing that you can do is have all the crosses here in the center of the big cross. The small cross is centered on the center of the big cross. We can get even information about aberrometry exams. So here you can read the spherical equivalent of the refraction measured with the total aberrometer. Here you have information about the total astigmatism, and here you have information about the pupil location respect to corneal vertex. So even here you have information about the repeatability of the fixation of the patient. So if these little crosses are close one to each other, you know that the fixation of the patient was stable. Once you analyzed all these parameters, you are even able to select which acquisition is your favorite, and for the next time you can decide to open just the star acquisition. So this was what I wanted to say, and thank you very much.
Thank you very much, Simone, for this excellent presentation. I really liked it a lot. Maybe I would like to give a quick comment to the end and to the audience that regarding SCC measurement, please make sure, as you all are all aware, that your eyes are really wide open, and when you blink before, that both eyes are wide open, and actually that we do cover one eye during measurements. But thanks again, and let's ask my colleagues Stefan and Ute, do we have any questions from the audience?
Yeah. Yes, there are two questions open. There was one question to Francesco Versaci. The question is, so one large spot consisting of perfectly uniform, let's call it pixels, is projected to the retina. Then it goes back to the pyramid as an image of the retina, where it's separated to 4 pictures, which represents each 4 quadrants. So basically, each pixel can be seen from 4 different perspectives, thus measuring its deviation from perfect wavefront. Correct? Yes. Comment, correct, please.
And the intensity of each pixel in the subpupil is the function can be read as a function of the aberration. So if I have some strong local tilt in this particular pixel, I will have one bright pixel in one of the 4 pupil and dark pixel in the other one. If I have equal intensity on the 4 pixel in this particular position, I will have a planar wavefront. So that's you are reporting correctly. I know it's a bit tough to be understood. It's not a simple principle. We spend a lot of time fully understanding this, but you were saying correctly. You were saying correctly.
Okay, wonderful. So the next question is related to the head position. The tilting of the head will influence the fixation of both eyes. How does Peramis get rid of the additional deviation?
Oh, the question was for Simone, but I think that I can answer to this. One eye is not measured, so the measurement of the topography is monocular, not binocular. So we can avoid to talk about the second eye because the placebo disc is very close to the second eye, and the image is very blurred, and so the second eye does not influence in any case the fixation of the measured eye. The fixation on the first eye is not influenced in any case by the tilting of the chin rest, because the eye orientates in the direction of the extinction point. So the patient is asked to fix a light projected from the infinity, so optical projected from the infinity, and so it doesn't matter what is the position of the chin rest. The eye always look at in the axis of the device. Maybe probably you can confirm this because you are a user also of the Sirius device, and you are a user of Topography since a long time. So.
Okay, fine. Then there was an additional question. What about trefoil aberration?
Mm-hmm. The trefoil aberration, it can be measured as all the other aberrations. So something that probably I didn't mention in detail is that actually there is not a real reason for using the Zernike decomposition, but the historical reason and the comparison with all the old exam. The Zernike aberration is something that, as Simone say, is something that is being developed to have a decomposition of the Zernike of the components of the wavefront, but the Peramis is able to measure the wavefront in his full components. If you remove all the Zernike, you will see that there is some residual that is still important. So the trefoil is one of the many other aberrations that we can measure, and is interesting because it has 3 lobes. It's very common in keratoconus or in the central wavefront, but is one of the many other aberrations that we can measure. So we do not make any difference between trefoil or quadrifoil or heptafoil or commas, secondary comma, and so on. So it's one of the many.
Okay, thanks. I think this was all for the moment.
Then I have actually a question that might be interesting for the audience. As Simone showed the refractive maps and how you can compare them, so differentiate them, the pre and post-op maps, could you determine the optical zone from there, from those difference maps? I'm not sure if you could hear me while you were changing.
No, sorry.
No problem. So I will repeat my question. So you showed on your presentation the refractive maps and that you subtract them pre and post-op. And can you see from this subtraction, can you determine the optical zone that was treated?
It is a good question. We should maybe the most accurate way is not using the refractive power map if you want to analyze the morphology. Okay, so if you need to analyze the morphology, I suggest to use a tangential map. Okay, if you want to analyze the diameter of the treated zone. If you want to analyze the refractive outcomes, you better use the refractive power map.
All right, perfect. And regarding dry eyes, what about artificial tears? What would be your recommendation prior to a measurement? Because I personally always, when I go out from the application part, I tend to not to use artificial tears if it's not necessary, of course, but sometimes if you have really dry eyes, it might be necessary. So what is your opinion?
And in my opinion, it depends of the composition of the eye drop. I mean, you cannot instill too much viscosity, too much viscous eye drop, because it can alterate too much the tear film. But if you have something like even saline solution or not so viscous tear, you can you can use it.
All right. Okay. Then, if there is no other question from the audience, Ute, your microphone.
There is one more question. How to acquire the higher order information to decide the treatment guide with Peramis? I would do it in this.
Is this for you? Sì, fa partire.
I would.
Can you hear me?
Okay.
Can you hear me now?
Yes, Francesco?
Yes.
Yes, we can hear you.
Probably this question is the same, has the same answer of the one that I answered before. If we can define some good metrics to evaluate the quality of the wavefront, and such metrics are the stress ratio, so the quality of the peak of a PSF, we can try to remove the high order aberration components and see what is the best, the optical best solution that minimize the size of the PSF or maximize the stress ratio. So beside treatment thickness of treatment consideration, I would suggest to find the highest possible stress ratio by removing the minimum number possible of Zernike coefficients. But as far as I know, you can do this probably in a better way automatically into your account software, because you have a way of optimizing the treatment by removing just some of the Zernike coefficients and optimizing the profile according to the saving tissue options. Is that correct?
Yeah, that's correct. Then I would just mention one more point is when you cover the eye, make sure that you're not really blocking it, because it's important that both eyes are open wide. Otherwise, if you block one, the other one cannot be open completely. So that's one comment I would like to give to this. So if there are no further questions, I would say thank you very much to everybody for participating here.
Wait, please, there.
Yes.
2 questions are coming in.
Oh, very good.
So, this meeting, give it to. Okay, the question is, with a keratoconic cornea, is the topography reliable if the corneal apex is decentered and measurement aligned with apex?
I would say yes. I would say yes. We have even a map that help us to describe better the shape of keratoconus. This map was not commented in my presentation. I'm talking about the Gaussian curvature of the cornea. Is a map that is not analyzing, as I told you before, meridian by meridian, but is constructed doing the average point by point of the 2 main meridians of passing through the point. So using this kind of map, you will have a correct representation of the keratoconus shape. So if you need, and it is the map that is displayed in keratoconus screening. So you can get information about curvature, let's say in general, with tangential representation, and a morphological representation of the ectasia provided by Gaussian map.
Okay, and the last question, is kappa angle affect topography K measurements?
No, I would say no. The only thing that we can note is a decentration of the keratoscopy respect to the position of pupil, but an eye K angle cannot affect the topography.
No further questions for Bart?
What? Some further or no further?
Further, if you want to correct the aberration with our laser with 0.56 millimeter of spot, cannot overlap the zone of treatment, so can change the result. Well, this is related to customized ablation, which will be topic in our next webinar. Let's see.
So what is the ideal light conditions in the room for a good exam?
For sure, if we are talking about aberrometry, the preferred condition is the scotopic condition, because we can get a bigger pupil and get more information. For topography, I would say we don't have indication about the light condition. The only thing that we have to avoid, let me say, is the incident lights on the camera of topographer. But having a scotopic condition is important just for aberrometry exam.
Okay. When we turn the patient's head, what are the tips to have a good static cyclotorsion?
This is a good question, Franci. Could wait it out.
Well, I think if I may comment on this, I think one of the most important point is if you're tilting the head in either of those directions, is that you have both eyes wide open. So in case the eyelid is in the way, the SCC is already probably not functioning very well. So one of my always what I do in the introduction phase is that before you click the measurement, you blink, you open both eyes wide, and then you capture the image. That usually should already do a good job for capturing the SCC. Maybe Francesco or Simone would like to add something on that.
This is Francisco lost his microphone, so he can just answer by moving his head. But
all right.
No.
But I think that should be fine.
Yes.
Okay. Now I can talk again.
Okay.
I would like to add something on the two previous questions. The first one about keratoconus. If the keratoscopy is not too bad, so if we can recognize the integrity of the rings, the measurement of the keratoscopy is usually good enough. So it's your duty to evaluate if the rings are correctly recognized and if the quality of the ring is acceptable for the type of measurement that we need to do. What you have to take care during the keratoconus, when you acquire keratoconus, is that at least the pupil center is reliable, because as you can imagine, the keratoconus has not straight fixation, so we cannot be sure that the patient is fixating all at the same point. So it's a good idea to check the repeatability of the pupil position in the quality summary map. This is tips that I would like to give the user. I fully agree with Simone answer about the angle kappa, because the angle kappa is nothing but the big decentering of the pupil center spectral corneal vertex, but this doesn't impact that much on the quality of the acquisition. It can impact actually on the quality of the export, because if the pupil is strongly centered, you might have more issue to reach the minimal diameter for the export, but doesn't impact on the quality of the keratoscopy itself. The last question was about, can you?
I think SCC.
For circumtorsion, I would also comment that it's important to explain what's going to happen, because during the Peramis acquisition, you have a small flash of light, and it is important to tell to the patient that this is going to happen, else the risk is that the patient can move during the acquisition, and you won't have a good quality of image in any case. So an explanation, talking with the patient and explaining what's going on is always important.
Yeah, very good comment.
Okay.
Stefan, do we have a last question from the chat?
Yes, a last question. Which factor is the first priority to choose the best image? I think this is related to the statistic.
I think we have to evaluate several parameters. There's not only one parameter to be taken into consideration. In my opinion, the most important things are the fixation repeatability, the alignment of the corneal vertex with the topography axis, the quality of keratoscopy, and the coverage of keratoscopy. And if these parameters are good, even the standard deviation of sync and astigmatism will be good. So in consequence of this, we have all good parameters.
Okay.
Okay. All right. Then I would say thank you very much for all speakers and the help of the SCHWIND people and the help of Iona in the back. So I appreciate it. Thank you very much. I hope the attendees enjoyed this session from CSO. I appreciate it. Thank you very much, Simone. Thank you very much, Francesco. And as Ute mentioned, we are going to having a webinar about customized treatments at one point, and you will, of course, all be informed about that. So have a nice evening, morning, wherever you are in the world. Take good care. See you hopefully soon. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.